So I don't know if I told you this. I asked Matt and Rose to do this too.
Oh yeah?
Yeah, yeah. So I actually have Matt's first one. His video didn't work, but I have his audio, and I can post that at some point.
Okay. Have you done Rose yet?
No, Rose delayed to quarter four. She's getting her MBA.
Okay. Oh wow, that doesn't actually surprise me. Actually, yeah, I'm not surprised.
Yeah, she's getting her MBA. I couldn't believe it. I'm going. Well,
Oh
actually, I could
wow.
believe it.
Yeah, no, that's the thing is
Yeah,
actually you're surprised and you think about it for a second, you're like, actually no. No, I believe that.
yeah. So Rose, she's doing that. So she's also engaged to be married at some point, if I remember right.
Okay.
You are married.
I am married.
Yeah.
Yes, I am. Yes, that was the simplest solution to our not having the same passport and wanting to live together. So
Yeah.
we
It's
do actually like each other.
oh, that's good. That's good.
Yes. So about it was 2 years this summer we've been married now. And
Two
he actually just
years.
started a PhD as well. So
Wait. So you're just getting to your postdoc, and this
yep.
guy. Oh my goodness.
No, so he worked, so we've traded off, which is actually quite good. So I did my PhD and he had a real person job, and then I now have a real person job postdocing. It's sort of real person job, and then he's going to do his PhD, which is good because I've had friends that have done it at the same time, and it's rough. Like you're both not getting paid very much, you're both very stressed, you're trying to write thesis at the same time. It's really good to have that person who's like, it'll be okay. I promise. Who's not actually in the like throes of it at the same time. So
Lifeline, right?
yeah,
Yeah, that's your lifeline. Well, that's good.
exactly. Yeah.
Okay, it's been about a minute, so I'm about
Cool.
ready to introduce you and get things started here.
Sounds good.
Okay, going to hot in five. Hello, everyone. Welcome to the podcast today or tonight, depending on what side of the globe you're on. In this case, for Stephanie here, our guest is going to be in the UK, and tonight we're going to be talking about her graduate experiences. She is a dear friend of mine from senior design in UC Davis, and in 6 years she's made a lot of headway, and I want to ask all about it. So let's get this started. Stephanie, thank you for getting on here.
Yeah, no problem.
So, the first place I remember seeing you, or the last place rather, I remember talking to you in person was June 2014,
Yeah,
and we were in a senior
graduation.
design. Right,
Yeah,
yeah.
right. Yeah, so last time probably would have gone graduation, but the last like class we took together was senior design.
So, I want to ask, and I asked this the same question to Matt, just so we can.
Yeah.
This is where we were on the same wavelength before we deviated. So,
Yeah.
what made our senior design function well? Because a lot of people didn't have that experience.
No, yeah, I still remember feeling like really blessed. Like the first time we like got together and we like started talking, I was like, okay, actually I think we're gonna make it through this. But I think when I was thinking about it, it was the fact that like we trusted that we were all different and we used that to our advantage, right? Because that's one of the problems you have with group dynamics. You've got different personalities coming together and how that's going to work. And we trusted each other to have skills and things that we weren't so good at, and it allowed us to sort of specialize in what we were really good at. Like I remember you let me do the presentation and I did a lot of like the writing stuff because I was quite quick at that. So I think I wrote the whole like report on that all-nighter. You were scanning pages and putting together the appendix, and Rose was costing things, and it was just like we all did our jobs, and it was really we got really lucky in that respect, I think.
I would say blessed is accurate. Uh,
Yeah.
yeah, it was a big thing on trust, and Jordan Pearson was talking about this in his book. It's one of the biggest revenues that you can actually utilize to get things done. Because
Yeah.
money only goes so far, but trust is
Yeah.
that's the foundation for how trade and other things to get. things moving works. And without the
Yeah.
trust, you wouldn't have the credit card thing. You wouldn't have money that doesn't not backed by the gold standard. There's a lot of trust there. Um,
Yeah, and I remember like if you said, "Hey Stephanie, can you do this?" There wasn't you weren't checking over my shoulder, right? You trusted me to deliver that portion, and the same went for everyone else, and that's hard to find.
it was, and there were so many people who had a terrible senior design project for that very reason.
Yeah.
And it was just trust. That's it.
Yeah,
That's
that
it.
was all it was. I just like I knew you were gonna like, "Hey, this is oh man, I did not enjoy that. What was the software's called again? I haven't used it in six
Aspen.
years. What was it? Aspen. Oh man, I was like, I am not very good at this, and you were like, I can figure this out, and I was like, okay, I
Yeah.
trust you.
I was surprised you guys let me use the Aspen machine, but I was up for it apparently. If it was MATLAB on the other hand, I'd be saying, "Hey Stephanie, anything you could do here with some of these hardcore calculations?" And you go, "Yeah, sure." Um,
No, I did end up doing a lot of the like calculations in the end. A lot of the paper stuff was all my handwriting. So
yeah, you did a good chunk, and I remember. So there were two favorite moments of mine in the library. Two. One of them was getting you ready for the presentation. It felt
oh
like,
jeez.
but that was so much fun for me because I did all.
It was
Here's all
like,
the prep work. It's done.
yep.
So it's
It was
just
like preparing someone to go to space, right? Like you've done all the like you got to send this one representative.
I liked it though because you were taking it in. It's just here it is, here it is, here it is. Everything's laid out for you.
Yeah.
And we thought about I'd say 95% of what they could say, and
Yeah.
it was pretty smooth. I was kind
No,
of in
it
my
did.
seat.
I remember I was like we were so nervous and like he didn't really have any like questions to throw at us because we'd accounted for like all the things that we thought they were going to ask us.
And then after that, there was a second part that I liked, and this was when you were more frustrated, but you still kept it together, which is, I think, even more important because this is where it really counts. This is like week 8, and we're doing
Yeah.
our redesign after being overhaul. So we got to do this big overhaul, and
Yeah.
so what material construction do you want for your distillation column? Stainless, please. And then fine, and then you put it into the Excel sheet. Okay, what do you want for how many plates? 30. Okay. And just and you kept asking me question after question and okay, here's your numbers. But
Yep.
but you just powered through it and we all did and
Yeah. That was a hell of a night. I think that's my no, it's not my last. Well, it's my last all-nighter where like I had like a due date. I've not gotten myself into that situation. I've worked some night shifts on the experiments, but that was my last like all-nighter. I've got this due tomorrow. Has to get done.
yeah, for me nights has been way more frequent. I've actually preferred it for what we've been doing. And thanks to that, it's allowed me to grow in the chemical and engineering industry in a completely different path because less people are overseeing you. So
Yeah.
that's been pretty slick. But today, I wanted to ask about the. Now that we've talked about where our last endpoint was,
Yeah,
I
we
need to
went
start
in.
asking where did it go from there. So you went to PhD school, and I'm going UK. That's all I know.
Well, basically, it was kind of a weird, like everyone was like, I applied for different jobs, and like I wasn't really sure where I wanted to go. And so Adam Mulay, you took the ECM6, the
I
MATLAB
survived,
course.
just like
You
you.
survived. So at the end of that course, he sent me an email and he was like, "Hey, did pretty well at my course. I'm looking for people to do undergraduate research." So I was like, "All right, I could think about that." So I did 2 years of research with Malay, and he went to I think it was the APS conference, and I forget where it was, but Adam Lay went with his poster and he met Dr. Andrew Parnell, who was looking for someone to come and do a PhD that they had for this grant in Sheffield. And Adam very nicely sang my praises. And I got an email from Andy being like, I know you were doing solar cells, but do you want to come to the UK and do this? And I was like, yeah, why not? That sounds like an adventure. And yeah, so I came over here and I did in and out. I had degree conferred in 4 years. They let me skip the master's even, so I just went straight into PhD. And yeah, so I finished that was in June. I was vivaed, which is my thesis defense, in June 2018. I had finished my correction in September 2018. And then I took 10 months off to go travel in Southeast Asia. And then I've come back and now I'm a postdoc back in Sheffield because I actually quite like it over here.
So Sheffield, is that technically England or Scotland?
That is in England.
Okay, England.
It takes you quite a few hours to get to Scotland. So I guess the simplest way to think about it is if you flew into London and you got on a train and you went due north on a train for 2 hours, you'd end up in Sheffield.
Oh, okay. So you're pretty much you're in England. Yeah, hands down.
I'm in England.
Yeah.
I'm in the county South Yorkshire, and Yorkshire is a very particular culture in the UK. It's like being a New Yorker, being a SoCal versus a NorCal kind of thing. So like Yorkshire is kind of like a bit of a rebel, bit of a outsider, and yeah, so I'm a Yorkshire person now.
I didn't notice it, but are you picking up a little bit of the UK accent?
I talk a bit funny. So I have spent 5 years in the UK, and I am married to an Irishman, so who I probably spend far too much time with.
Huh. Yeah, I was wondering. You sound a little different. Maybe that's why.
That is it. I think, yeah, it happens. I mean, because I was a military brat and I moved every few years, I got used to kind of picking up the like local like slang, I guess. And so I think it happens a bit naturally. Plus, every time I say capillary, if I say capillary versus capillary, I get made fun of. Or if I say aluminum, they're like, "Do you mean aluminium?"
Aluminium.
Yeah. So I say capillary, and I say capillary and aluminium, and I say bin instead of trash can because that people make fun of me for that.
Yeah. Oh, that's so American. Yeah, I can see that.
Exactly. Yep.
Well, I wouldn't change very much, so I'd be a big target if I went over there. Keep that in mind.
Oh, we just got a visiting researcher from South Carolina, and he's like, I very much hear the accent now that I didn't used to hear. So
Yeah, South Carolina. Oh, they'll eat him alive. That's
yeah.
great. So those were all. So that explains a lot because I didn't know you were that connected to the professor in undergrad, Adam. And
I mean, I was on a paper that was published by one of his PhD students, and it really was Adam. And he sat me down. He said, "Hey, I will write you your recommendation to Stanford. I'll write you your recommendation to MIT, but I think you'll be miserable there. You'll be there for 5, 6, 7 years, and I could send you to Sheffield. You'll be well treated, and you'll be in and out in 4 years with your PhD." He was absolutely right.
Huh. Well, he made for his promise. That's good.
No, he did. He really did right. Ooh, there we go. Sorry, my computer screen died on me.
Wait, can you still see?
Yeah, no, I think it just went to sleep for a second.
Okay. Yeah, I got my phone here on my right leg so I can look at the questions. So this brings us to the next question. So undergrad, grad school, there's not really that many differences, right? Or not many similarities, rather.
No, really, really very, very different. Like, so the UK is structured a little bit differently. So I guess just for your viewers' understanding, if you go to apply to do a PhD in America, you would generally, kind of like undergrad, apply to a university, get accepted. And then from there, you kind of find a PhD supervisor. You usually would do like 2 years of courses, which would constitute a master's. In that time, you sort of develop a research program, and then you go from there. And it's rather open-ended. You could research for 2, 3, 4, 5. I know one of my colleagues was American, did his PhD in Indiana. It was 7 years. So it's a very loose kind of structure. The UK, in order they advertise a specific PhD position for a specific project with a specific supervisor, you apply to do that. Your application lands on the desk of that professor. It doesn't go through a general university admissions. You apply to do a PhD with that professor on that project. And then if you get accepted to that, if it's a funded PhD, which it typically is in STEM, then you go straight into your research. There can be sort of these programs where maybe you need a bit of extra funding and then you'll do a little bit of teaching, but you're not going to be TAing, you're not going to be marking unless you want to. You can to pick up some extra money, but it is 4 years of research and you're paid, not a huge amount, but paid. And you don't really take any classes unless your professor is like, hey, do you want to sit in on these lectures that may be useful to you? There's no grades. You pass a 1 year confirmation review, and then you write a thesis and you pass your thesis defense, which they call your viva over here. That's it. You do research, and it is much more. I've not had a true job outside of academia, but I imagine it is much closer to having a job than it is to being in school, if that makes sense.
Yeah, so your job really is like university based, and you're working for the university more than you are feeling like you're in school.
Yeah, I
Yeah.
know, and it's real self-taught. It's not, there's not really a textbook, there's not really a logical it's if you have an experimental PhD, it's go into the lab, try this. When it inevitably doesn't work, try 10 other things till you find something that works. And yeah, it's your job, but it is really nice in the fact that it is flexible in the fact you set your own working hours. You see PhD students that come in at like noon and work till like 8 p.m. and that's just what they like to do. You see the ones that come in really early, get their stuff done and go. It is, yeah. So it's a job, but it's a very flexible job.
Yeah, we were talking about that before this. The strategies of coming in early so that way you've got the lab to yourself, or
Yep.
staying late for the same reason, or maybe
Yep.
just doing a normal schedule so you can see more people. Uh,
Yeah. So I kept it reasonably normal schedule until I started writing up, and then I realized that I really needed people to not be bothering me. So I would come in really early and I would do all my writing in the morning, and then I would make graphs and stuff in the afternoon, which was a little bit more like people could ask me things and talk to me and it wouldn't break my concentration as much.
okay, so but there was a point with writing that it's it may be 6 in the morning, but I gotta get this out.
Oh yeah, I was writing 2,000 words a day. I was writing a chapter a week. I knocked it out very quickly because I was just like, this needs to be done.
Man, you kept the work ethic. If anything, you got it sharpened even more. That's cool.
Yeah, when I moved over here, my professor was like, are you going to keep your American work ethic? And I was like, what? And apparently, Americans really have a reputation over here for working a lot harder than your average UK student.
Darn right we do. Yeah, there's something about it. The culture is work till you drop still.
Yeah, I have to say, I have kind of gotten used to my cushy European work ethic.
That happens to a lot of people, though. Even in the United States, depending on what job you get into, sometimes you just get into a spot where, okay, it's comfy enough, and I'm not going to have to go full throttle, and that seems to be easier on my family and then on my social life. So, yeah, no, I can run 70%. Yeah, I can do
Yeah.
that. And I think that was a lot of our goals, actually. But in undergrad, for me, that was the time to let it rip. Go all out, 100%. Every step you make may give you or take you into a different spot where it's stable. So I had no reason to slow down then.
Yeah.
But when I got out of it, definitely, I was, man, could we crank it down a little bit? Especially after I talked to you when I was overseas. I'm going,
Yeah.
this is crazy. I gotta crank
Yeah.
this down, even for the United States. This is some 80-hour weeks were no joke. I mean, you got a week
Yeah.
off every now and then, but it was It was something else.
Yeah, no, I remember people talking about the sort of chemical industry just burning through their new engineers, like just burning through them with the amount of work that they were being asked to do.
And what specifically?
But just like you were saying, those 80-hour weeks and the week on, the week off kind of thing, you burn out quickly, I think. I mean, I was warned. I mean, Adam Malay told me to take the summer off before I started my PhD, and I didn't. I stuck around and I wrote and I did the paper, and I felt it. Like I definitely should have listened and taken that time off, which is why I took the time off after my PhD, because I was just like, I'm gonna burn out by 30. Like,
Yeah, please. Yeah, and you didn't. You didn't. You took the time off in Southeast Asia,
yeah.
and
No, I came back really ready to do research again. I think the end of the PhD, I was like, oh, I need a break. And yeah, I've come back and I've really jumped into things and I've really been enjoying it. And they say that like you should do a postdoc and think of it about as basically like a reward for doing your PhD. You don't have to write a thesis again. At most, you have to write a few page manuscript. Like it's
so
not quite the same pressure.
oh, for sure. So a chap. How long were you writing a chapter a week for?
Oh God, so I had a lot of experimental chapters and I even cut a bunch of stuff. So it was probably a month and a half. I was really only doing the chapter a week at the kind of end when I really needed to like, I just gave myself a deadline. I was like, I just need this out the door.
So it's more like 6 weeks of intensive writing, but then there was all these other experimental portions where you're doing uh,
Yeah.
neutron experiments and X-rays and
Yep.
it, yeah.
Yeah, I mean, I took an unbelievable amount of data. I did one experiment where I took 10 terabytes of data in 3 days.
Terabytes.
And then it terabytes. And then I had to learn how to program a supercomputer, and it took me a year to analyze the data. My entire third year, I took all the data from my PhD in my first 2 years. My entire third year was analysis.
The entire year. So you spent one
Entire
year.
year.
So this would have been, let's see here, 2014 to 15. So 2016 to 2017.
Mm-hmm.
That time frame.
A
You're
whole year was me in front of a computer, learning how to program a supercomputer. I needed I needed 200 gigabytes of RAM to put the matrix together. Yeah, it was unbelievable stuff.
I guess that makes sense to keep the somewhat okay ratio to run this thing.
No, it was
Or
just the actual physical size of the matrix. Even if you had it in int 8, where you were just sort of like the minimum bytes per thing, right? Per number to hold it in, it was just so big. It was a three-dimensional, it was basically an MRI, but using X-rays for something really, really tiny. And yeah, my matrix was like 1,000 by 2,700 by 9,000 points.
oh, there you go. Okay, so 10 terabytes. That,
That was the raw data of everything we took. And then each individual scan was 53 gigabytes. And then there was 6 to 8 scans per sample that I had to put together, which made a matrix. And then some of my calculations, they had to be floats, which means you have to use more bytes to store each number, which means the matrix goes up to like 400 gigabytes. Crazy stuff. That
yeah.
was my entire third year.
So the only thing close I've even gotten to that is on video. So if let's say we had to stream this, or not stream this, let's say we had to record this on my like a hard drive.
Yeah.
So we'd rack up 125 gigabytes at this pace in about 52 minutes.
Yeah.
So in your case, though, that's wildly to the other end of the spectrum. What kind of
Yeah.
supercomputer do you use? This isn't even on the questions list.
It's just a cluster. So basically, the university maintains a cluster where different research groups will pay for different nodes. And the idea is basically like, okay, I need this specialized node that has 700 gigabytes of RAM, but I don't need to use it every second of every day. So I pay for it and then I pay for part of it, and then the university maintains it as part of a cluster, and then you can write scripts for a job, and then that gets put on the system, and a scheduler independently kind of puts these jobs on these different nodes when it has time. You get priority on like the ones you paid for. So I had to get special permission from the math department here to use their like fancy, really high RAM nodes. It was very nice of them. Because my group doesn't really do this kind of stuff very often, so we didn't own like a node that I could use.
But in your case, that's good, right? Because that's an opportunity. That's like, okay, if people in this sector is not really doing that, this is
Yeah.
exactly what a PhD person could be doing.
Yeah, no, I definitely showed that you could do an analysis on a big data set like this, and you could get a true average of a structure that most people, so before this, the only data that had been published was one tiny little cube of this structure that was like 7 microns by 7 microns by 7 microns. And I measured like 30,000 microns cubed of this entire structure and was able to computationally average and find sort of like an average cube that I was then able to show how that physically develops in the beetle based on fundamental physics.
Wow. So 30,000 microns. Okay.
Cubes, yeah.
So in cubes. Okay. Yeah. It's great because you're actually using some kind of metric. We
Yeah.
use that standard sometimes with polish filters.
Yeah.
But that's crazy. 30,000. So before it
Yeah.
was only 7?
7 by 7 by 7, so 200 and something, yeah.
So you got to really zoom in on that thing. Now you can actually just see it.
Yeah.
That's great.
Yeah, no, you can see the whole scale. So like I think the paper was published. It took a year to get the paper published. The paper was published in August 2019, I think. That makes sense?
Yeah, you're really
Yeah.
excited. You posted that. You're going, look, I
Yeah,
published.
yeah, geez. I think we added it up personally. I think we got rejected like 9 times before it actually went to review. So it was a long process.
Wait, 9 times in like a period of a year or in a period of
Yeah, in the period of a year. So you write it up, you send it out, and then usually you don't get past the editor. So the editor will be like, no, this is not good enough, or not the right fit, or not interesting to our audience, and it gets bounced back. But that process can be quite slow. So you send it out and it gets rejected. And you send it out, it gets rejected.
So how'd you hold it together on like that 6th revision, 7th revision?
It was starting to get, so basically we aimed high as far as like a really high impact kind of prestigious journal, and you start kind of knocking it back. And it was getting to that point where we were like, oh, do we just send it to some nothing journal that'll definitely accept it, just so at least the work is out there and then people can discuss it? Because part of the problem was that I may have slightly been counter to previous literature, and that previous literature might have come out of Cambridge University.
Oh, a big one.
Yeah. Ours was the first instance of measuring this thing completely intact, where it hadn't been cut open before it was measured. And it turns out that quite changes the answer. But I think that was hard to get across, as to people were like, oh, this has been done before. No, this hasn't been done on an intact piece of this material. You need to do it this way and this kind of stuff. So that was part of the problem. But we finally got there. We ended up in Nature Communications Chemistry, which was a new journal, and it doesn't have that many submissions going to it. So I think that worked in our advantage. But it's really just nice to have it out there. And I mean, it's had over 2,000 people download it at this point. So it's nice.
That's worth, yeah, that's better than
Yeah.
nothing. That's 2,000.
Yeah, it is.
So for the viewers, what exactly were you actually trying to measure that was intact? Was this the bugs thing that you were talking about?
So my project was inspired by the idea that titanium dioxide in white paint that's where most of the carbon footprint of paint comes from. And the idea was, could we replace that with something synthetic that doesn't require being mined out of the ground and refined and all these sort of nasty processes. And there was this two particular beetles, the Cyphochilus and the Lepiotostigma, and they're these sort of they have these vividly white scales and they're really, really thin. They're like 12 microns thin or 12 microns thick. And they scatter like 80–90% of light that hits them, which is just unbelievable. And the way that they do this is they have a porous structure inside the scales of these like kind of interconnected rods. And yeah, I think of like a coral, like sponge kind of structure, kind of like that. And light scatters when you have a refractive index change. So every time there's an interface between air and the material, it bounces the light off and it just gets really, really scattered all around. And the idea was, okay, well, how do they make that? That was my original task. But it turned out that when I went into the literature, there wasn't a lot of consensus on like what actually the structure was. Like what is the percentage material to percentage air? Just that simple number was all over the place. So like it turned out that I actually had to do this crazy characterization with X-rays to get this massive data set just so I could understand what actually my target parameters were. And then I was able to match this to something called spinodal phase separation, which is basically two liquids separating when they become unstable. And then I matched it to that. And I showed that computationally you could generate these test structures, compare it to the beetles. And from there, I was able to actually make a synthetic version of this white color. I was able to make films, and I think it would be another project to try to make it into like particle spheres that you could actually put into paint. Well, that was the sort of the journey, 4 years of my life in about 2 minutes.
No, that's good because I remember you said something about I'm going to be doing something about these bugs that have this white pigment like stuff in their shells, and if we could do
Yeah,
that synthetically, you're in. Yeah,
yeah,
I remember that much, but I don't remember
yep.
what bug it was, or I didn't even know like how you're just gonna anything about it other than there is this particular bug. And if it's proprietary, I
Yeah.
understand you don't want to say it. That's fine. But I
Yeah,
wasn't
no,
sure.
they're actually just a pest in Southeast Asia. They like eat sugarcane crop.
Oh, even better. So
Yeah.
who would have thought a pest would actually have something valuable if we could actually
Yeah.
get it to be synthesized?
Yeah, exactly.
Are they to the point where it's you can get like billions of them, just surrounding a particular sugarcane pile, or is it like
They are definitely a pest. I didn't focus too much on the like biology side of it. In fact, there's an entire another question that needs to be asked, which is why have these actually ended up white in the first place? What was the evolutionary driver for this? Because both male and female are white, so that indicates it probably wasn't sexual selection. So why actually they ended up being white is actually quite a mystery.
huh? Yeah,
Yeah,
because there would have been something to drive that particular color for them to get.
color, yeah.
Because
Yeah, so it's
otherwise,
not like a beautiful color on a bird or a butterfly that signal to the other sex. They're both white, male and female. So quite puzzled on this actually, and I think it's something we'd like to investigate at some point.
so there's actually a few other questions that still are really out there. Oh, that's cool. So
Yeah, definitely.
so let's say you had to train some another PhD student at some point. You really could point him in that direction if you wanted to.
Yeah, no, I think the postdoc, Andrew Parnell, who originally brought me on the project, is still really interested in this. So it's not the focus of our current grant, but I think we would like to put together a project to investigate that in the future because it's something we're both quite curious about.
See, and here I was thinking that, oh, we have it solved. We've got the whole matrix thing figured out. Now you still have the biology aspect, the how would we even harvest it on a small scale so that way you can actually put it into the paint.
Yeah,
Yeah.
how you would actually encapsulate it is actually the problem. So I can make a film of it, but how to get it into a particle that you could just sub in for titanium dioxide is still something we have some prototype, but it's still something that would really have to be thought about from a formulation perspective.
Yeah, and you're one of the few people here. So there's a lot of environmentalists out there. You're one of the few people that are actually doing something about it in a way that's like, oh, cool, we don't have to mine anymore. Here, yeah,
Yeah. So I actually use cellulose acetate, which you can get cellulose as like a derivative from like plants and stuff. So plant fiber could be used in this instance as well.
cellulose. Yeah, that's super common. I mean,
Yeah.
and the acetate group, is that forming naturally, or is that just?
I think that's synthesized. Basically, I was it's the equivalent of you remember transparency sheets with overhead projectors.
Yeah, yeah.
Yeah, I was basically dissolving transparency sheets and turning it into ultra white films.
Oh, okay. Well, there you go. That's
Yeah. So you could think about possibly recycling sort of like single-use thin plastics as well.
so just for getting cellulose acetate. I mean,
Well,
again, another
but so the
recycle
thing
project.
is, well, no, but the thing that I showed was that the way that it phase separates is actually a universal process, basically. So anything you can dissolve in a liquid that you could get it to phase separate by adjusting parameters like concentration, as long as it has an unstable, unmixing region, you can get it to phase separate. So in
Hmm,
theory, you can do this with a lot of different polymers, any type of plastic, really.
that's something to consider. That's cool.
Yeah, it was a good project.
Well, what's cool about yours? I didn't know it could spawn so many other ones. That's what I'm
Yeah,
taking in right now. Here I was thinking this is kind of an isolated thing. It's not in the slightest. So,
yeah. That's kind of how like these grants happen is, you do one bit of research and then you go, oh, what if this? And then that spawns the next thing and it kind of you'll actually kind of see these sort of like parent chains where like someone did a PhD and then the next person took over on that project and the next person took over on this project. You can kind of go back through this like family tree of who did their PhD after who.
huh? Yeah, I'll keep that in mind. Um, so all these experiments you're doing. Okay, we were talking about X-rays, and you're talking about the
Yep.
neutron. Tell me about the
Yeah.
neutron thing, the neutron beam.
So, I do a lot of experiments at these so-called like big facilities, which are basically so they're either for the X-rays they're synchrotrons, which are big rings, and you fire electrons, and every time an electron turns the corner, it basically emits an X-ray, and so then you get these X-ray beams. And neutrons are it's a neutron reactor, and you get neutrons, you get a flow of neutrons out, and you fire them at your sample, and you get contrast between things. So in X-rays. Um, Heavy metals scatter differently than sort of organic material. So you get contrast between that. And then neutrons, it's scattering length density, which doesn't scale with sort of the weight of the atoms at all. It's kind of random, and no one's really got a good theory of what predicts this. But yeah, so I do a few different types of neutron techniques. The one I was doing recently in France was neutron reflectivity, where you basically bounce the neutrons off a surface, and it's really sensitive to sort of really thin layers. So it was for a PhD student in our group was looking at how he has a layer he puts on top that's active in water. So he's actually watching that layer of material rearrange when it came in contact with water.
Okay, so
We were having a lot of trouble aligning the sample. We couldn't make that interface between the water and the sample.
so if you're firing a neutron beam, is it really easy to miss because it's so small? Or
Yeah, it's you have to get your optics just right. So it's so you've got all the optics set up and you've got these detectors that are like huge. I mean, these huge tubes and all these complex optics. And you've got the beam coming through, and the beam has been optimized by loads of different things, by choppers, which sort of cut down the wavelength ranges and all these different things. And basically, yeah, you have to scan your sample in different orientations. You have to, align the angle and the tilts and everything else so that you're definitely hitting the sample where you think you're hitting it. And that can be some of the most time-consuming part of these experiments is making sure that you're hitting what you think you're hitting. Because sometimes you hit the edge of your like sample holder, and that is not useful data.
so that's the equivalent of, okay, well, my sample is in the middle, and then you're hitting like the spokes holding it up, or Like
Yeah,
what?
pretty much. One time I was doing an X-ray experiment and I had mounted my sample with a bit of blue tack,
Go on.
and blue tack scatters really nicely and you get a very pretty pattern, which is not what I was looking for. So I took some interesting data on blue tack by accident.
How long did it take for you to figure out that, oh, this isn't my sample?
Pretty quickly, because my sample was pretty boring. You basically would just get kind of like a ring, and blue tack has these like all these different crazy patches because it's got order within the blue tack actually. So you see that pop up really quickly and you're like, that's not my sample.
So, with these neutron beams, you're how do you have to reset? Do you have to like stop it? Is there like a
So we have these big shutters, so you get big lead shutters that come down, and that stops the beam coming through. So you can actually go in. I mean, so you get your Geiger counter out, sort of open the hutch, and you make sure that there's no counts, there's no neutrons going through, and then yeah, you can go in and do your sample, and then you basically they have all these safety procedures. We hit the search buttons, and you lock the whole thing up, and then you're able to open the shutter, and then you have neutrons. So usually there's a constant flow of neutrons from the reactor, and yeah, you just you got to wear a dosimeter, and you got to like follow all these safety procedures. And I mean, you're generally classed as a non-exposed user when you're in the like computer, like the control room. You
right?
shouldn't really, yeah, you shouldn't really be exposed to anything unless something goes terribly wrong. But yeah, it's got lead shielding and all the like beamline hutches and all that kind of stuff. Yeah, it is nuclear material.
Sure. I mean, you probably have some kind of nuclear fission going on in
Yeah,
the
yeah.
upstream, so you can have your neutron beam.
Yeah, so it's just an honest-to-God nuclear reactor in France.
That's cool. But
Yeah.
so in order to actually stop the neutron flow, it's just a lead plate, and you just put it
Yeah,
down.
it's just a shutter. Yeah. You just close the shutter.
Okay, so in the chemical engineering world, we'd call that a gate valve. Got it.
Yep.
It's a lead
Yeah,
gate valve.
exactly. It's a lead gate valve.
That's pretty slick. Okay.
Yeah,
So,
it's very stressful though because it costs an unbelievable amount of money to run these facilities, right? And so basically the ILL, it's in French, so don't ask me to say it,
sure.
but it is that facility is owned by France and Germany and England. And basically you as a scientist will put in like a proposal. I'd like to use this particular instrument to do this. I need 3 days of time, and it goes to a panel and it gets ranked, and then you get allocated a certain amount of time, and these go on cycles. So maybe you might get one shot at these experiments, and so you run the beam 24 hours a day. You have one shot, and it could be that your PhD depends on this data set, and it can be very stressful.
Wow. This is some so when you get in there, that there is like all hands on deck. Do you have any help when
Yeah.
you're doing this? Do you have like people manning
Yeah,
machines and
so you have your beamline scientist, which is it's usually there's a technician that supports a beamline, but then you'll have an actual beamline scientist who is someone who's familiar with not just the instrument in terms of its mechanics, but what the data is supposed to look like and how to actually maybe do the measurement that you're trying to do. And they're unbelievably important. You rely on them so much. And, if something breaks at 2 in the morning and you got to ring them and be like, hey, the heating stage isn't working, the liquid pump isn't working, this kind of stuff. A good beamline scientist will make or break these type of experiments. So it's a hugely important job, but it's very hard because you are on call 24 hours a day when your scientists don't know how to use the instrument.
yeah, so essentially the neutron beam is highly booked. You got a lot of
Yep.
PhD students that want to use it for their experiments.
PhD
It,
students, professors, postdocs, industry, like, yeah, everyone wants to use neutrons are precious.
oh, I'm
Sometimes
sure.
it's one of those times that you think about like when we did like experiments in like our like project class in our like lab classes, right? You always had to do repeats, you had to do it 3 times and this kind of stuff. It's pretty well accepted with neutrons that like if you get one run, that might just be it. You might just have to publish that because that's probably the only one you're going to get.
Wow. Okay. So the reloading process then, if you got to put on like a new sample, could you get more than one sample? And
So if you're lucky, you can rack it up in an automatic sample changer and then load a bunch of them in at once, and then you get to go home and sleep. That's the best case scenario.
Yeah, that's the best case. Okay.
Yeah,
How
does
long?
not always happen.
Oh, I'm sure. I'm sure. And I can only imagine how long you have to keep the neutrons actually on target firing.
Yeah, it's very slow. So you don't have that many neutrons coming. And the way that you build up a data set is basically you just turn a detector on and you just count for like hours until you build up sort of a distribution of where the neutrons have scattered off your sample. So yeah, so like one measurement, I mean, the instruments have improved massively over the years. Back in the 70s when they first started doing this, you were like 16 hours to measure one thing. Now you can maybe measure like basic sample in air in like 2 or 3 hours is probably, you'll get enough statistics off that.
Cool. So let me see if I understand this. So you've got a lead gate valve that opens. This neutron beam
Yep.
fires at your sample.
Yep.
The neutrons scatter all over the place depending on how it hits. Just like light would, it would scatter
Yes,
once it hits a particular refractive surface. And
exactly.
then you measure wherever the heck these things go on some
Yep.
kind of like parchment or wait, how do you? Yeah, you
No,
got like
I mean we have some very fancy. They're fancy cameras basically. They're pixel detectors now, and you count intensity at each pixel basically. And then of course all of this is happening in inverse space. So that image you get is completely in inverse space. So then you have to try to fit it and understand what that actually means in terms of real space. Or sometimes you have to know the answer in order to get the answer, which makes it quite difficult.
oh sure. I mean, come on, how many? Well, I think my physics problem means 23 kilonewtons. Okay, let's plug it back to find out what the mass was. Oh wait, aren't I
Yes.
actually solving for this? Oh yeah,
Yeah.
yeah.
That sounds, yep, pretty much. So there is one neutron technique that I'm one of like less than 10 people in the world who have actually like used this technique because it's really out there, but it does actually manage to, it uses the neutron spin in a magnetic field to actually take it back into real space, which I really liked because then I was like, this is actually a real space correlation to my sample. So that one was quite fun.
So on that particular run, you actually got it first time. You didn't have to invert it. You didn't have to do anything. Just whatever the intensity pixels were taken by those cameras. That's it. That's the
Yeah, so
graph.
you get what's called a correlation function, which if you ever wanted to do the math, it's the Fourier transform squared inverse Fourier transform Abel transform that gives you a correlation function. But that is your real space correlation function. So if there's a peak at 2 microns, then that's where that is. It's not 1/2 pi of that.
I haven't dealt with Fourier transforms since 2012, and that was only an introduction because we got like 2 weeks of it, and then it showed up on our final, and then
Yep.
we were. Well, I'm glad. I was glad to at least review it one time because that's all. Like the neutron beam. That was the only chance I got. So Fourier transforms show up in this.
Yeah, they absolutely do. So basically, what you're doing when you fire an X-ray beam, if you just do a standard SAX, which is just fire it straight through your sample, and see where it scatters in this direction, in this direction, circular. That is basically doing a Fourier transform of your material.
Huh. Never would have thought of
Yeah.
that.
Yeah, so that is the Fourier transform of your material.
I've learned quite a bit today. Wow, this is so far the most interesting thing's definitely been the neutron beam. And so what else did you get to do with this thing? You said liquid pumps, so I bet there's definitely some heat transfer going on.
Yeah, so one of the ways that you can generate like contrast between your sample and the environment is to use deuterated water. So
Oh, heavy water.
heavy water. Yeah. So basically, you can pump. So we were pumping in deuterated water, so DIO, no D2O. Sorry, we were pumping in D2O, and then you pump in like combinations of that, and by changing the amount of heavy water to your regular water, you can sort of match the scattering of different things. So this PhD student, we were doing heavy water, regular water, and then he had a bunch of silica in his thing. So he worked out the ratio of heavy water to normal water that would give you a similar scattering length density to silica. So he was matching different bits of the sample so you could see different things happen. So yeah, so you have to do contrast changes, and the pumps are all automated. Sometimes the pumps wouldn't go, and then we wouldn't get a contrast change, and then we'd have to figure out what had gone wrong with the pump, and it was sucking air, and then you had to suck all the air out of the pump. It was a pain.
Wait a minute. Hang on a second. You said you gotta suck the air out of the pump. What are you using, like a siphon? You did a siphon motion.
Literally just you would hook it up to the pipe, and then we had a syringe where we would literally just like pull air. Yeah, you suck the air out of the pump.
Yeah.
It was late, and we just had to get it done.
I see.
Yeah.
Okay. Yeah, the pumps. I take it they're not that big then if you're using siphons.
No, exactly. We're talking the flow, the cell volume is maybe in like less than a milliliter. So we're not pumping very much because deuterated water is actually rather expensive.
Sure, meter that in carefully.
Yeah, exactly. Yeah. So.
Wow. Okay. Yeah, so, have I asked you enough questions about the neutron beam?
I mean, technically, my current position is a postdoctoral research associate in neutron scattering. So, I'm supposed to be an expert in this.
Oh, good. Okay. I may ask you about it later, but I think for now,
that's absolutely fine.
So you got to use the neutron beam. Okay, that was 20 minutes. What other? So, did you use anything complex as far as X-rays, or?
Yeah. So I mean, my X-ray tomography experiment was pretty much my favorite experiment that I've done, and that's that 3D MRI that I took all the data on. And that's basically, you imagine if you can see through something, right? And if I can see through it at every single angle, right? You should be able to back calculate a 3D structure that would give you that see-through image at every single point. That makes sense?
You got it at every point, though. That's the key.
Yes, you have to. That's why the data sets are so big, because you have to have it. I took 3,000 different angles, and then I had to do it a different. We moved it to and from the camera, which changes basically the focus. So then you can get different focuses, and that also helps understand where the edges are. Yeah, so it was unbelievable. I had to mount a beetle scale, which is 200 microns tall and 12 microns thin, perfectly straight on the tip of a needle. Because you had to be able to spin it in 360 degrees. So, yeah, that was three months of my life I'm never going to get back.
So, like a pin needle or like
a pin needle, like a sewing needle.
Did you have more than one so you could kind of keep it balanced while you turn it every...
No, I glued it to the tip of a needle.
Okay, glued to the tip of a needle, and then the needle's on like a post that you probably also glued?
No, yeah, so you mount it on the tip of a needle, and then you put it into a pin, and then you glue that down, and then this pin gets set on this basically massive marble slab, because you need everything to be really still, and this gets magnetically locked into place. And the way you move your sample is literally by like pushing the magnet to and from. You don't even have electric motors to move it because it's not repeatable. So you basically just push it into position, and then that just stays put and it spins.
What's up with the marble slab then? Is this just for density?
It's just stability, just a big heavy single slab, and you put all of your like electronics and your camera on this like big slab. It might not have been marble. It was a big stone slab that everything was sat on. Okay. Yeah, it may not have been marble because it's expensive, but I just remember it's just a big stone slab. Everything locks down, magnet drops, and yeah, you can just kind of push it into place, and then everything has to be ultra stable, because if your thing wobbles like this while you're taking the picture, well, that's going to change the answer, isn't it?
Unfortunately, yeah, because you
and you miss one angle in your data set, like now I've got a missing like line through that image. So
yeah, and again, the assumption is you get the entire 360 degrees.
Yep.
And then you got to get in So whatever 3,000 divided by 360 is.
Yep.
Yeah.
And then you got to do the different distances. And then when you do the different distances, you want to align them all. So ideally, the same pixel in each image to be aligned. And because my sample was amorphous and it didn't have like really defined spots, I had to align all the images by eye. So yeah, I actually had to write a Python code that clicked back and forth to flip the images because I was getting carpal tunnel in my wrist from clicking back and forth and trying to go flip it back and forth. Okay, that moved left. Oh, that moved up. Like, yeah.
So you mentioned the images. Were you taking particular images to help you figure out exactly where this thing was, or?
So you're taking X-ray projection images is basically just like X-rays, just like an X-ray of like your hand, right? You don't just see the front, like you see everything in between all overlaid together. So that's an X-ray image. So I'm basically just taking ultra powerful X-rays of this thing at every single angle, and then using that to back calculate the original 3D structure.
Which you were successful at, which is
We were.
Yeah.
We were down to 25 nanometers a pixel,
And
which
and
is
and this
very
thing is,
small.
but this thing was on the micron level, but you could get down to nanometers.
Yeah, so each pixel was 25 nanometers.
Got it. Okay.
Yeah.
So spinning it on a needle, you had to keep it exactly straight. Just one needle. I'm still like, just one.
So basically what I would do is I would scrape the scales off the beetle, and then I would scrape them onto a microscope slide, and then I would look down the microscope, and then I would put the beetle scale so it was hanging off the edge of a slide, and then I had a micro manipulator to move the needle. And I would bring the needle over, dip it in a bit of glue, come back, touch it to the end of the beetle scale, and then I would optically cure the glue, and then hopefully that was perfectly straight when I tipped it up. Took a lot of practice.
I'm sure. Like, did it take 100 beetle skins of gluing, or?
Yeah, it took months of practice. And in the end, I could maybe mount, like, because it had to be perfectly straight, because again, there was no motors to like tilt, bring it into alignment. It had to just drop it in and be what it was. So lots of practice, really.
So you couldn't even just start this. You had to. I need to get the skills needed in order to first put it on
It
that
was,
X-ray.
I mean, it starts even before that because you need to figure out what instrument, this was the only instrument in the world that could have even done this were these two instruments at the SRF, which is the synchrotron in France. You got to write the proposal, you got to hope that get accepted, and then you got to call your beamline scientist and be like, how do I mount these samples? She was so funny. So she sent me an email. She's like, mount them perfectly straight on the tip of a needle. And I was like, okay. And then she went on holiday and then came back, and then we showed up for the experiment, and I like brought her these pictures of like these scales mounted on the tip of a needle, and I was like, is this going to be good enough? And she goes, I honestly didn't think you were going to be able to do it. Yeah, she was like, the backup plan would have been just to drop it in a capillary and see what we get, but obviously then you would have been having the capillary and the beetle scale, so you would have had interference from the glass at the edges, and you wouldn't have gotten as good of an image. So
Sure, you got crap in the way.
yeah,
And
exactly.
and then you'd have to, okay, take this part minus, oh, that would have been worse
Yeah,
for
no, exactly.
$3,000.
I would have had to reconstruct the glass around the sample in order to understand what I was seeing, which would have cost me a lot of resolution probably.
Oh, I bet you couldn't get 25 nanometers with that. I mean,
No, absolutely not. So it was the only way it could be done, but it was definitely not an easy task.
yeah, I hope you saved that email. That's like legendary. It's history in the life of Stephanie.
Yeah. I
Yeah, hey,
think I have a lot of patience.
that U.S. work ethic paid off, man. That's the one thing
There you go.
that's
That's what it
it.
was.
So, so was the X-ray? This is the last question about the X-ray.
It's fine.
Is it like a 360-degree X-ray, or is it just you just shoot it like
It's
like one 2D?
it's like a square. So this particular type of X-ray tomography requires a coherent beam, which means you've got all your wavelengths the same, and it needs to come at it in like a block. So it just goes straight through, and everything goes through at the same time, so you get the right image at the other side. And that's only really possible at a synchrotron.
Okay, so but it's a block X-ray.
Yeah, it's like a square.
Gotcha. Okay.
I mean, you can do it like line by line. Well, you could scan down your sample line by line and build an image. And you could also, I mean, scan it pointwise. But the beauty of this synchrotron was that you could do the whole square at once and get just an image like that without having to do a scan. I mean, it still took 45 minutes to collect one projection series. And then I had to scan down the sample because you only have a certain field of view.
So 45 minutes, 3,000 angles. How many?
No. So 45 minutes to collect to 3,000 angles. That's
Okay.
what it was so amazing. Is because the synchrotron is so bright, meaning the X-ray intensity is so high, you can expose for like a fraction of a second and get a full projection image. And then, so you're really only limited by the speed you can save your data, the speed of your motors, how fast you can do the motor movements, and how fast you can save the data.
Got it. So actually, when you did get it perfectly straight, I mean, boom. I mean, you had in 45 minutes.
Oh, I had a scan,
There it is.
Yep.
But it took what, maybe 1,000 iterations to do, or?
So collecting the data was 45 minutes, and then the actual data processing, that's got to be done on a supercomputer again, because it requires so much computing power to use all of those projections to get a 3D structure out of it.
But now it's in that paper and you can use it.
It is. And so like we published the paper on like the physics of it, and then I suppose I should hear back from the editor soon. I've put together a paper that is just the data, the big data set, so that hopefully other people can use that, because I worked really hard on that data set, and if someone else had something clever to do with it, I would love to be able to help them do that. So hopefully that should go live in the next few months.
Here, take it to the next level. Here's everything I've got.
Yeah, exactly. And I think because the previous group that measured that 7x7 cube, people have asked them, they refuse to kind of share their data. And I'm like, that's not really how science is supposed to work. We're supposed to build on each other's achievements. So we're going to put the data out there, and I really hope that someone else finds something cool to do with it. So I'd love to see what people come up with. So
this is so cool. You're doing what science was supposed to be. Here we've achieved this. Now go forth, and maybe it could be used for something even more, as opposed to locked in a study somewhere.
Exactly. And I mean, I spent literally years of my life collecting this data set, and there's no reason anyone else should go through that same pain and suffering when the data set exists.
And that's exactly what education and doing a PhD is all about. It's the passing down of data. And then now they can actually do something.
We all just make these tiny little steps in our field, which are like so insignificant, but you never know when it might be useful to someone else.
My co-host Julian's going to love this. So incremental steps is a recurring theme that we've talked about.
Okay.
So I think there you go, Julian. Another one that's coming straight from Stephanie. It's important. It's one of our themes, because getting there, it's not like, oh, I just made it through the X-ray machine. It's no, I had to get it just right. I had to get the approval. There was this journey to get there.
Yeah.
So, and you can't do that unless it's incremental. So 1 foot at a time.
Yeah.
Man, years of this. That's crazy. So now that I've asked about the X-ray, the neutron beam, were there any other instruments that were absolutely needed for what you did in your research?
We kind of are a scattering group, to be honest. So, I mean, I'd use sort of your basic lab equipment, made solutions, spin coded, and this kind of stuff. But if you go through my chapters, I did some electron microscopy. That's just to like get some microscope images, and then it basically went straight into neutrons and X-rays. I did small angle X-ray scattering, which is where you just shine it through. And these measurements are super fast. And I actually watched my films that I made develop. So that was like an in situ measurement, and we watched the dynamics form, and I was able to track what was happening in the sample. I did that one, and the X-ray tomography, and CSANS, which is spin echo small angle neutron scattering. And yeah, a lot of computation. That was definitely the core of my thesis, were those 3 experiments, and then a lot of computing power.
Oh, for sure. I mean, so let's see here if I can name supercomputers. You got the neutron beam, the X-rays,
Yeah.
and now I didn't know about the electron microscopy. So you're taking an electron microscope and you're going really far down to the point where
yeah. So SEM is scanning electron microscopy. So you scan a beam across the sample, and you know, based on where that beam hit, you then put that to a camera, and you know you'll get contrast again between electron density, and you'll be able to see different things. That's been around for a long time. That's better. It's getting around the optical resolution problem with light. So light is limited to the 2 points you can resolve based on the wavelength of light, and then electrons have a much smaller wavelength, so you can resolve smaller features.
So are you seeing molecules, or are you seeing more of just the...
No, not molecules. I think that you can use, I don't really do much AFM, electron force microscopy. I think they have in the last few years, like you actually saw it on a poster recently, you can actually image like a bit of the helical structure of DNA, but that is sort of where where we're at. Oh, yeah, a lot of people there's so many different research groups that spend an unbelievable amount of time just trying to improve the resolution of different types of microscopy. It's a massive field.
Oh, that's good to know. I mean, if they got the DNA though, that's something else though. Because I mean,
yeah, no, it was a really cool image, like super resolution microscopy, where basically you basically make things blink. So instead of trying to measure the light all at once, you measure individual points that blink on and off, and then you do this over a period of time, and you can build up an image where you can resolve the individual ones because they're turning off and on. Just kind of neat.
So you have to compile a bunch of images, not just take your camera photo of it. Got it. Okay.
Yeah, so a lot of these things are really slow. So like AFM, it needs to scan every single line across the surface. So the end goal for a lot of these things is to be able to do it fast enough that we can watch stuff happen at these sort of really small length scales, which would be really cool.
Okay. Wow. I have to learn something about micro. Yeah, all that's zooming in. But in your case, it was more for just getting an idea of your sample, or...
Yeah, I was trying to measure it without cutting it open. So that was why we had to do the tomography on it. And then so because we couldn't watch the stuff forming, it was with a microscope on that length scale of sort of like, sub-microns. That was why we did the X-rays, and that was where we got to watch the dynamics happen, because you could do it so fast. We were exposing for a fraction of a second, and like I said, it was just limited by how fast we could save the data.
Okay, so saving the data was your limiting factor. Okay, good to know.
Yeah.
So that'd be sad. Like I got exactly what I wanted. Oh, I only got this much.
Yeah, so you have to save each frame after it's taken, and the save time limits when you can take the next image.
Okay. Beyond me. Wow, that's... So I wanted to ask, did you do the QE? If you even just went straight to PhD over...
I just went straight to PhD. So they basically, because I had 2 years of experience and I'd published a paper and I'd sort of shown my research credentials, there actually is no formal is not required to have a master's to do a PhD, not even in America.
Huh. How about that?
So yeah, they just let me skip it. I mean, it's kind of tradition actually. So like one of my friends went on to do a PhD at Duke in South Carolina, and he basically had finished his thesis, and his supervisor was like, no, you got to write part of that up as a master's thesis. And he's like, but it's kind of just like everyone else had to do it, so you have to do it. But they were happy to take because they only here undergrad's only 3 years, and you usually do a 1-year master's. So our 4-year undergrad course is quite intensive. And they were pretty happy to take that with my research credentials and straight to PhD.
So, wow. So you're telling me the chemical engineering undergrad in UC Davis was actually like that was a big chunk of, oh yeah, we trust you.
Yeah, well, that and the fact that I did the 2 years of lab experience. I mean, doing the undergraduate research really was really important in the end. Everyone kind of made fun of me because Malay couldn't afford to pay me. He didn't have like the money to pay for a PhD for an undergrad student, but I did it all for free, and it's really paid off in the long term. So
I know. I mean, you get to be in who would have thought you would have been in Europe in
I know,
2020, you know?
I know. I was just in France. I was in Grenoble. I'm 2 hours on a train to London. I go down there for conferences and collaborators and crazy. It's definitely not the life I thought I was going to live. I feel very blessed. Like,
Yes, you are. And for
yeah,
what it's worth, those 2 years, you just got it paid later. It wasn't,
yeah,
it was delayed payment for sure.
yeah, exactly. No, I mean, people were sort of, I mean, shocked because I know that a lot of the other people that were in our chemical engineering class, sort of at the top of it, doing like research for professors, were getting paid. And they were like, what are you doing working for free? And he did right by me in the end. So I feel very grateful for that.
That's a good redeeming factor for the professor you worked for because a
Yeah,
lot of
no,
other people would have said
absolutely.
otherwise.
Yeah, no, it's very true. But it just, I just definitely have to say thank you.
That's cool. So, was there anything else you wanted to add as far as graduate experiences that, like the highlight reel, overcoming things? You said a lot already, but
I have said a lot. I mean, I've been through this recently because my husband Killian was deciding to do a PhD. So we sort of talked through like, why would you do a PhD and what are some of the hardships? And like, I think you have to accept when you go into a PhD that it is not like undergrad. There is no structure. There is no textbook. There is no like exam where there's a right answer. It can be very uncomfortable for people when they first start. I mean, I saw my like professor like once a month. And in between that, I was supposed to figure stuff out. And at the end, that ended up being like the perfect fit for me. It was my thing, it was my work. I was basically self-employed. And it was really rewarding to have freedom. The idea is to make an independent researcher. That is what they're trying to do with a PhD, is they want to make an independent researcher. And the way they do it is basically just to drop you in the deep end and see who swims.
seems
It's a
to
hard
work.
thing to teach. Yeah, no, it
Yeah.
does. It does. And a PhD varies massively. I feel very fortunate. I had a really good postdoc on my project, and I had my professor was kind of over there thinking about the big picture in the world, and my postdoc was really like there for me day to day. And if you don't have that support, I think it can be really, really hard to get stuff done.
Yeah, I would say so. I had another graduate student on here early on a few months ago, and he was talking about, yeah, there's something different when you're going into uncharted waters. Um,
Yeah, the PhD wouldn't be funded and paid for if they knew the answer. They're paying you to figure it out. So they don't actually know if it's going to work usually.
so it's really an adventure in that sense of you're going on an exploration. So see what you can
Yeah,
find.
it's definitely a journey, and like you look back on it, and a lot of people look back quite fondly, like upper academics will reminisce about their time as a PhD student. It's a weird time in your life. You have like nobody's expecting you to show up, but at the same time you have stuff you need to do. You have a lot of freedom, and yeah, not a lot is expected of you in the beginning. So they do give you that opportunity to grow and find your feet. Um, the first year, you basically know nothing. And you fake it till you make it. The second year, you think you know what's going on. And then the third year, you realize what you actually should have been doing for the last 2 years. And you scramble, and then you write a thesis.
Okay, so that's the actual cartoon version of what's going on.
Yeah.
Okay,
Yeah.
it's cool to hear it that way because there's a lot of people, and actually, that same guy was talking about imposter syndrome. I saw in your notes,
Yeah.
same thing.
Yeah. No, I was like really lucky that my postdoc was so good about pushing me to apply for this conference and put in that abstract. I'm like, but I don't know the answer, but it's not good enough. It's not ready yet. And he's like, no, you put it in. And yeah, some great conversations came out of Like my first talk I gave at a conference in Manchester, about a year into my PhD, and I look back on it and it was so bad. But like important conversations were had, and different directions were thought of, and this kind of stuff. And yeah, you do just have to accept that you are on the low end of your field in knowledge, but you have to still go for it. It's uncomfortable though, because you're surrounded by all these people that are just brilliant on the top of their field, have written the textbook on what you're supposed to be doing, this kind of stuff. So yeah, it's hard. And I would mental health is a huge problem in academia. It's really well known that it's hard on your mental health. I mean, most of my friends have said, like, once you pass that Viva, you feel like a different person, like the amount of weight that comes off your shoulders. Because unlike a job where if you work in a job for 4 years and then you decide to leave, you've still got those 4 years of experience. But if you do the 4 years of the PhD and then you don't actually get the PhD, what do you put on your CV to fill that, in your resume to fill that gap? Like you have to get the PhD at this point. So it can be very, very stressful, especially if you have major corrections on your thesis or you fail and you have to be revivered. There are some definite negatives. I feel very fortunate that mine was relatively smooth. I passed with minor corrections and it went quite well, but I have friends that it didn't go so well, and part of that was not a very good supervisor. It's not a very well thought out project, and there are some things that are outside of your control. So if anyone was thinking about doing a PhD, and clearly my husband and I have been through this recently, we vetted his supervisor. I asked everyone I knew at the university, I was like, is this person a good supervisor? And yeah, he's like won awards for like supervisor of the year in that department and this kind of stuff. And my supervisor thinks very highly of him and respects him. And it was like, your supervisor matters. So choose your supervisor very carefully. Your project could be kind of, but if you've got a good supervisor, it's like having a good boss. It makes a huge difference in your quality of life, doesn't it?
Darn right. I got one now. Yeah. And it took a long time to get to, by the way. For the first 4 years, it was the bosses. I'm going, oh, that's actually one reason why I got pushed when I got to night shift and they said that you want to go, and I said, yeah, I'll do it. Yeah. Because I didn't have to deal with that anymore. And it's been, but now that I've got a boss that has been he's on the respectable level. He cares, and that changes because now you've got backup.
Yeah, and that's part of the reason I came back to Sheffield. I took my 10 months off and I applied for a few other jobs. I got offered a few that I just did not get the right vibes from. Quite a bit of problems with my field is not very well known for being rather feminist. So there were I got basically told, well, since you're a woman, you'll get promoted and we can't fire you. And I was like, well, that's not the place that I want to work. I want somewhere where I'm valued for my contribution, not just as we need to get our numbers up kind of thing. So that's why I ended up back in Sheffield. Good people are hard to find, and definitely have some good people in Sheffield.
Good. Yeah. What the heck? And let's say it happened to me. I'd be pissed too. I'm going, I just show up and win. That's dumb.
Yeah. No, it doesn't feel right. No, it doesn't feel right. I didn't really appreciate that. So Sheffield, I know I'm valued in Sheffield for my contribution for science, and that's what really matters at the end of the day. I do love my job. I like doing experiments, and I like collecting data, and I like fighting with massive data sets and programming, and it's kind of everything. And I've recently been offered the opportunity to actually lecture, so I'm going to get to teach an undergraduate course next semester, so I'm pretty excited. You remember all the tutoring that I did.
I remember.
Yeah.
But what are you going to teach?
I'm going to teach solid state physics. It's kind of a conglomeration of a lot of different stuff. So you'll have kind of the materials like lattice structure, and you'll have waves and semiconductors and sort of that kind of stuff. So
there's a practical aspect about that. Yeah, semiconductors for sure. I mean, they're all over the place.
Yeah.
So.
Yeah. We've actually, someone in our group has recently developed a coating. This is crazy. Not sure I quite understand the physics, but basically it takes solar cells can only collect a certain portion of the spectrum, right? So it's really good at collecting red light and really bad at collecting blue light. And this material actually takes blue light and turns it into one blue photon into two red photons, which then can be collected by the solar cell. So you can actually just spread this on an existing solar cell and like double your efficiency. It's really cool.
And then there you have it. It's just, okay, there's your red.
Yeah. Yeah, one blue to two red. It sounds so simple, and then they get into the actual like physics of it, and it's yeah.
Yeah, usually
Kind of
trying to make
crazy.
something simple, you have to do a lot of work to get to that point.
Nothing is simple.
Yeah, I agree wholeheartedly. I mean, when we explained
Yeah.
our senior design, for example, that, yeah, it's simple. You just go through these three reactors, then you go through this distillation
Yep.
column. Before you know it, there it is. There's your methanol.
Done. Yep.
Except not really. If you actually follow the chain and you see all the inertians you have to do and the startup and all of the design work, it wasn't that at
Yeah.
all. So
Yeah. See, and you stayed in chemical engineering, and I did that design project and went, I think I need a different field.
well, I'm glad you got into a field you liked. I got into a field I could do,
Yeah.
which to me that's a win for me because believe me, when I got into chemie, I was in over my head. I'm like Luke Skywalker in Episode 4, way over my head. Farm boy that's doing space battles, not really what's going on, right? So for me, to be able to do something and be pretty good at it after practice is just, all right, I can roll with this. So, and it's been a good journey for me too. A lot of bad parts too, though, and the mental health in chemical engineering, as you know, isn't always so great either.
No, it's not. So that's keeping on the up and up and making sure that you keeping yourself in a place that is comfortable for you mentally is really hard because it's not easy, is it? It's not easy, especially when you're trying to do a really hard job.
Yeah,
Like you said, it's a job you can do, but it's a hard job. Like at the end of the day, like I got very lucky that I just Adam met Andy and they're like, oh, you should come do this. And it ended up being something that I liked. But it still is a hard job at the end of the day. And you have to remember to take breaks and take care of yourself. So there
right.
you go. There's your mental health PSA at the at the end here.
Yeah, well, Matt and Rose and yourself did that for me, and then I think I would like to believe I did it for everyone else in return.
Yeah.
Um,
No, there was definitely we fostered a good camaraderie during that of keeping everyone sane. I think we all had our moments.
we did. Whether it's Matt can't get his R&D stuff straight, or it's Rose that I don't even want to work on economics today. Please work on economics today.
Please.
Just
Rose who's gonna go do business. You need to do the economics.
That's right. She's doing
Yeah.
her MBA, man. Like you can't just drop it now. This is
No.
And then if I just drop the Aspen, you're like, we can't do anything now. We
Yeah.
need those simulations.
Aspen was a black box that I never managed to crack.
That's fine. That's in ancient history now. And for what it's worth, that's really more for steady state processes, which I don't do. I'm actually in
Yeah.
batch and semi-batch processing, totally
Okay.
different. So, and that's for the pharmaceutical industry, and it's like giving them the raw material they need for all the APIs that
Yeah.
we make. So we're more of a raw material company. Here you go. Here's your drum of 50 kilos.
Steady state's not interesting anyway. It's all in the dynamic.
It's not. It's not interesting because then it's just okay. It's running, and then it's
Yeah.
you know what happens when there's no hard problems anymore. Now it's about the petty stuff that's going on during the day because that's what's changing.
Yeah.
That's what you're going to focus on.
Yeah.
So when there's something
No,
hard,
we love dynamics as a group. You measure the static sample just because, but we want to see things happening. It's where all the fun is.
couldn't agree more. I hate a lot of the dynamic stuff, especially when it's, oh, we're going to do this new process and we don't know anything about it. Oh, great. What's the likelihood that the batch record, the quality representative, the client has no idea what's going on? Hi. Okay, so I'm on my
That
own.
sounds
Got it.
familiar. every time I work with industry people, they'll be like, they'll send me a material. I'm like, do you know what's in this? And one of them literally told me like, well, we put all the chemicals in a bucket and we get something, and it's not what we think we should get based on the chemicals we put in, but it works. I was
Oh,
like,
it works, huh?
cool.
Yeah.
Or they sent me a chemical one time and I was like, I asked for like a pure material and they're like, this has like 12 different components. I hope your analysis can cope. No, it can't, but thank you.
Yeah. Next.
Next.
Well, Stephanie, was there anything else you wanted to add to this? We essentially got through most of what I wanted to get through
No,
on the
I
questions.
think I think we got through all the notes and more. So yeah, it's been really fun. It's been fun to catch up. It's been a long time.
Been a long time coming.
Yeah, jeez, it went so fast actually. Now that I'm like 6 years, really?
We were in different frames, so it makes sense. Anyway,
Yeah.
I'm gonna go end the stream real quick, and then
Okay.
from here, it's been great. So thanks everyone
Yeah,
for
no, it's
watching.
been a lot of fun.
Okay.